yesterday. So here's the formula. Sure you had it written, but that's number 1. Alright, your definition doesn't have to be, like the Webster dictionary definition or the textbook definition. Any sequence that has a constant difference is a great definition for an arithmetic sequence. Or you could say any sequence that has a pattern of addition or subtraction. Very specifically going up by the same amount every time or going down by the same amount every time. Definitely not showing a pattern of multiplication. Okay, so if I want to write an equation for a sequence, I must know A1 and I must know the common difference. So what's A1 in this sequence? -3. And what's the common difference in this sequence? -5. So A1 is always the first value in the list. And the common difference is the change that you observe. This is subtracting 5 every time. So that's the common difference. So as long as you know the first term and the common difference, you can write an equation. So plugging into the formula, looking at a test for like Wednesday next week. Do you want to have this memorized by Wednesday next week? Plug in your first term, your common difference, distribute to the left to simplify. I'll give you half credit for getting this far, but I want to see you write it in simplest form. So this would be plus a -5n plus 5. -5 times n, -5n. -5 times 1 would make it a +5. And then you can always combine like terms when you're writing these equations. And here's our equation. This is an arithmetic sequence equation, but it's the same as a linear function. As a linear function, it would look like this. Right? In next chapter, we're going to do these same problems, but we're going to call them linear equations. So the curriculum wants you looking at sequences and recognizing them as sequences, and then we jump into a whole chapter where we call those same patterns linear equations. So, oh, okay. So, can anybody tell me where this 2, the 2 in the equation, where this 2 would show up in the sequence? Where is 2 in the sequence? Kind of an extra challenging question for you guys. Yeah, it's the 0 term. The number that would become in the 0 spot. So these are positions in a sequence. This sequence starts at -3, jumps to -8, -13, -18, and it goes to infinity. The 3 dots means it goes to infinity. This is the first term. This is the second term. This is the third term. This is the fourth term. When you do your formula and you rewrite it, the number that shows up in the equation is the 0 term. It's if the list started at 0, what it would be. Okay? And that makes sense when you think about the math. If you were to plug 0 in for n, you would get -5 times 0, 0 plus 2 is 2, right? So anytime you put the number that it is in the list here, you get that value out, including the 0 term. All right, let's use the formula. The 63rd term. So some people will subtract 5 63 times. Happens every year. They don't know the formula, but they get the pattern, so they're just like, okay. And they just subtract 5. And if it comes out right, I give them a little bit of credit. Like, that's the concept. A little bit of credit. Okay, so I'm going to use the equation. So I'm going to write, so I'll rewrite the equation. There's our equation. I'm going to do A with a little 63 equals -5 times 63 plus 2. A with a little 63. Nothing mathematical, just telling anyone looking at my math that what I'm finding is the 63rd term. That -315. -315 plus 2. Our 63rd term will be -313. And I do want this little guy in your answer. So look at what you boxed. If you didn't box, and make sure that you labeled what your answer is. The 63rd term. Okay, I'm going to walk around and see how many of y'all made a graph. Added this number 5. Graph this sequence. You don't have to graph the 63rd term. Let's graph the 4 that we're given. You guys need to put your devices away. Your devices have inspired me to take a walkabout. The next time I walk about, if your device is on your desk, I'm going to grab it. You don't want me to do that, so just put it away. You don't want me to grab your phone. Some people really don't like that. Really heated up in this class, but let's just say there's been some interesting moments when I've grabbed phones. It shakes things up. Looks like we have to go very negative. Wow, not shut it off. Try that again. So I could label this X and Y like we always do, but since we're doing a sequence, I'm going to label this N. In the Y-axis, A sub N. The ordered pairs that I'm going to graph. I'm going to do 1, comma, -3, because -3 was the first term. 2, comma, -8, 3, -13, and 4, -18. Okay, one thing that I did mention yesterday, I told you a lot of information yesterday. In sequences, we don't connect the points. So make yourself a little note. It's kind of like in the ultimate tell as if this is a sequence or a function. Sequences, we don't connect points. Oh, there's another thing I want to talk about with the graph. So the common difference that created the sequence, this -5 pattern, should show up on the graph. So -5 isn't a part of these numbers. Where's -5 on the graph? Where does -5 show up on this graph? It's an important part of the pattern. Should show up here. Anybody besides Thomas? Thomas, you have the other answer. Brianna? That's the rate of change. Good job. So this -5 is honestly everything. It's the whole pattern, right? So if you have a picture of the pattern, you should see it. So it does show up. It's the rise over run. So -5 over run. Instead of rise, I would call it fall over run. So I should be able to count. It goes down 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. Okay, so make sure that when you're graphing, your rise over run, your rate of change, your slope is the same as the common difference. Okay, full review of what we covered yesterday. Let's look at your homework.